Okay, so by the way, the rest, if you have questions, feel free to send them to me. I will try my best to answer them. But also, it will be better if you send it to me maybe throughout the week. I'm normally very busy on Saturdays, so I won't really have time to check my messages. But on normal weekdays, sometimes I have 1 hour free here, 1 hour free there. Then maybe I can answer some of your questions. Okay? To not take up too much of the class time. Okay, so this question is from, so if you want to follow along, this is from Summer 22, paper 22. Okay, so this question, right, you are asked to find the phase difference and the path difference for the two waves superposing at R. Okay, so at point R, the light wave will travel, this is R. The light wave will travel from here and reach R, and then the other side will travel from here and reach R. Okay, so they're basically asking you what's the path difference. So the first thing I want to identify is the central bright fringe. Okay, so central bright fringe, the path difference for central bright fringe is 0. Because the light that came from the slits will have the same distance traveled. So the light coming from here will travel, okay, maybe I'll draw a straight line. The light traveling from here to here, from the first slit to the point O, will have the same distance as the light traveling from, let's say, here to here. Okay, so from the slit to O and from the slit to another O, these two will have the same distance. So the path difference is 0. Okay, and then this means when I travel down, when I get a dark fringe, this dark fringe is lambda over 2. Okay, or 0.5 lambda. Because think about the conditions for superposition. When I want dark fringe, is 0.5 lambda. So then this one would be 1 lambda. And this one would be 1.5 lambda. Okay. So this one is basically the progression. Okay. And then the reason why I know it's 0.5 lambda and 1.5 lambda, this one will require you to think about how the wave should meet. So maybe I'll pull up a simulation here. You need to understand the principle of superposition first. So let's start with this random. Need a bit time for it to load. Are we loading? This one. Okay. So right now, you see two waves. Depending on how they meet, you either have constructive or destructive interference. Okay. So let's say I have these two waves, and right now, they have the same phase relationship. And to make it easier, I'm just going to start them both at 0. Okay, roughly lah. Now use degree. Okay, I cannot really get 0, but I'll try my best to get 0. Okay, so this one is like you pretend this is 0 and this one is 0. Okay, so this one is 0, this one is 0. Right now, they overlap perfectly. You get constructive interference. So this is bright fringe. Okay, so they overlap perfectly. Red plus green, I get blue. So that's why here I get bright fringe. Okay, same distance. Now I'm going to move one of the wave. If I want dark fringe, then it needs to be completely cancelled. So when I move, now I move the green wave and I move. Let's say I move until here. Okay. And then if you look here, the green wave and the red wave is 90 degree apart. 90 degree is also quarter cycle. See, quarter cycle. So this is lambda over 4. I move another quarter cycle. This is half a cycle. So at half a cycle, or 180, it will perfectly cancel out. Okay, close enough. 180 is perfect cancellation. So look at my green wave. My green wave was here, and now it has traveled half a lambda. So that half a lambda is this 0.5. Okay, let's keep moving the wave. Let's say I travel another half lambda. Quarter lambda, I don't get anything. It's not a pattern. Okay, so I travel another half lambda. That way, I get another bright fringe. So remember, I started from here. So when I move one cycle, my green wave would have moved one wavelength. Okay or not? You look at the green wave, it has moved one lambda. Constructive law. So this is for this one. Let's move another half a wavelength, half a cycle. There we go. Now we get destructive again. So this explains why each variation is 0.5, lambda 1.5. And then if you want to the next one, let's say there's a next point here, it would be bright fringe. And this would be 2 lambda because it will be 2 complete cycle. Is that okay? So this is an important concept to understand because it's frequently asked, the relationship between path difference and whether you get constructive interference, which is also called bright fringe for light, or destructive interference. Okay, the next question. The next questions is a comparison or a statement question. Aaron, you do questions can provide year and variant next time when you send them to me. Next time lah. Because if not, people want to follow along. Yeah lah, all 2022, but which year, which variant, which paper? Okay, so anyway, which statement is not correct for both forms of wave? I'm not quite sure. Not quite sure what's your confusion. I guess drawing it will help. You have transverse and you have longitudinal wave traveling both in the same direction down a long stretch spring. So instead of me drawing it in a very strange way, I shall find a picture on the internet. But we expect you to be able to recall it in your brains, I guess. Actually, because I'm a boomer, so when I was a student, I have to be able to draw it out lah. But the way I draw it out is not going to be as nice. So I tend to use this. Okay. So I can show both transverse and longitudinal wave on the street. Okay. So you basically, in my brain, I already have this picture inside my brain. Okay. So which statement is not correct for these two waveforms? Displacement measurement for the particle are made right angles to each other. So for this case, because my particle move up and down, and this is my equilibrium position, this is the displacement of the transverse wave. So here to here is SY. Okay. And then if I want to measure the displacement for this wave, so this wave is a little bit hard to visualize because it moves like this, correct? So because it moves like that, when I measure displacement, let's say this is the center of compression, okay? And maybe this particle is traveling very far. I actually measure the displacement this way because it oscillates this way. So this is the displacement. Okay, so this one displacement for transverse wave, this one displacement for longitudinal wave. Okay, because the particles vibrate 90 degrees, so the displacement is 90 degrees. Okay, energy transferred is in the same direction. If I put my hand at the same place and the wave travel in the same direction, then yes, well, it will travel in the same direction. Okay, the velocities of the two waves are in the same direction. Yes, because the velocity is also direction of energy transfer. Direction of wave propagation or energy transfer. This is your V. Okay. So they are obviously in the same direction. So these two is correct and they mean the same thing. So the answer will be D. Okay, because when we want to measure wavelength, let's say I want to measure wavelength for this transverse wave, I will measure from here to here. This is lambda. Actually, they label already lah, so I don't need to label. They measure from here to here. This is lambda. And this one, they measure from here to here, also lambda. So this one is wrong, lor. Wrong. It is parallel to each other. Okay, so we cannot anticipate the type of statement questions that they can ask you, but you just gotta trust your brain. Trust your brain that you can figure it out by thinking carefully about the statement. The more predictable one are always calculation. Okay, this one is May, June 22, P23, I think. What is the question about? It is basically a diffraction grating question that we can rotate from end to end to measure the maxima. And you are asked to calculate the number of maxima detected as the detector move 180 degrees. Okay, so we can use the equation. Whenever I see diffraction grating, I will use the equation d sine theta is equal to n lambda, right? So if I use d sine theta is equal to n lambda, then I can substitute the values inside, which looks like you have already substituted. And you find that n is equal to 5. Okay, so for those who need a bit of help, whenever you use d sine theta is equal to n lambda, first thing first, I got to figure out what is my d. So this is 2400 lines per mm, meaning d would be 1 times 10 to the power negative 3, 1 mm, divided by 2400 to make this thing. Okay, so I substitute into the equation d sine theta equal n lambda. Okay, so step 1, I know that sine theta must be less than or equal to 1. So this means my n lambda over d is less than equal to 1. I'm looking for n because I want to find the number of maxima. I have lambda given in the question. What's my lambda? What's my lambda? Where do you get lambda from? I'm guessing from the previous part. See, this is why you must tell me where the question come from, or else I cannot help you. No, I want to need to show people because you are not the only one in class. Maybe people never see this question before that. Okay, so I'm guessing it's this paper. I don't know. Okay, so at this point here, you are already shown the wavelength. Okay, so B part 1, you already have the wavelength. Basically, in the same question part, you have to find the values that you have to use. Let's say for part B, they will label it at 1, 2, 3. So part 1, part 2, part 3 is all related. Part B and part A may not be related. Okay, so my lambda is 8.1 times 10 to the power negative 8. This D is, this D is already calculated. So 1 times 10 to the power negative 3 divided by 2400. Okay, so I'll just multiply, okay? I'll multiply it on one side. So this will be 1 times 10 to the power negative 3, 2400 divided by 8.1 times 10 to the power negative 8. So you will find n less than 5.14, which is what you calculated here. Okay, so the order the maximum order is 5 because n is an integer. So the integer that fits this inequality is 5. So now I'm going to draw the order. Let's say I take orange to show the order. Okay, so we're going to start from here. This is 0. This one is n equals 0. So n equal to 1, n equal to 2, n equal to 3, n equal to 4, n equal to 5. Then here you have n equal to 1, n equal to 2, n equal to 3, n equal to 4, n equal to 5. So in total, how many bright spots do you have? 11. Because you have 5 on top, 5 below. So 5 times 2 plus 1, your central fringe. Okay? So that's why it's 11. So remember to count the 0 order as well because the question is number of maxima detected. So you will definitely have 1 in the middle. Okay, the next one. The principle of superposition says a certain quantity is added. We add displacement, not amplitude. Amplitude is maximum displacement, but it is not displacement. I don't know what's the confusion here. So displacement is distance of the wave particle from equilibrium position. Think about the definition. So we are adding these distances. What? No, meh? Let's go back to here and stare at the principle of superposition. Okay. Are we adding them together? You add the displacement. You add the displacement. For example, this dot plus this one, like 0 green plus a little bit positive blue and positive red is the same point as blue. We're adding the wave together. Do you know what is amplitude? Amplitude is maximum displacement. So amplitude is only this point where my cursor is, or this point where my cursor is. This point is not amplitude. 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 But we still add the points together, right? So it is displacement. Okay. So amplitude is maximum displacement. So it's only for one fixed point. Unless you're talking about stationary wave, then you could have, then there will be a different discussion. You do more questions first, lah. You may encounter them later. Okay. For this one, it says that observable interference fringes are produced from double slit, and the intensity of the light emerging from each slit is the same. So I'm going to draw a double slit. This is I, this is I. Okay. So the intensity of the light emerging from one slit is now reduced. Okay, so I reduce. So I think what will help you brain this is because you need to think about constructive and destructive interference. I guess a way to think about it to help your brain instead of using the intensity I is to use the amplitude A. Let's say this is A, this is A. So for bright fringes or constructive interference, we have the amplitude A plus A, which is 2A. But now I reduce one slit. So let's say this one, I reduce the intensity, it becomes A over 2. And then we'll say reduce by how much? So I just reduce by any number that is convenient to me. In this case, the bright fringe will be A over 2 plus A, which is 3A over 2 or 1.5A. So we went from 2A to 1.5A. The bright fringe becomes darker. Sorry, bright fringe becomes darker. Okay, let's look at the dark fringe. For dark fringe, I will have A minus A, which is 0. But for here, the dark fringe will be, let's say A over 2 minus A. I'll get negative 0.5 A. Negative here just means it is the throw of the wave. So from here, I can tell that the dark fringe becomes brighter. Okay. This one is also a very common question. It's helpful to just test values so that you know the changes that happens. Okay. But the idea here is the reason why dark fringe is brighter is mainly because there is no complete cancellation. I cannot cancel A with 0.5 A. So this one is due to incomplete cancellation. A over 2 is a number that I come up with because the intensity is reduced. So the intensity reduced means amplitude reduced. I reduce by A over 2, you can reduce to any value that is less than A. Doesn't matter. Does that make sense? They say reduce intensity, so I can reduce intensity however I want. Okay. You have a lot of question, or? Okay, let's continue. So two electromagnetic waves have a wavelength of this much and this much in vacuum. This one have to memorize one. Normally, I don't have methods for, I don't know how to memorize. Memorizing is not, if I'm good at memorizing, I would have teach bio. Bio is way easier to teach than physics. So this one you memorize, lor. Okay? Just memorize. The notes that I provide is fairly accurate already. So refer to my notes. Because mine is a direct copy from their textbook. Refer to my notes. You know where to find my notes or not? It's in Google Drive. Refer to my notes. Okay. This question, it says that wavelength of sound in air may be determined using stationary waves. In one experiment, a loudspeaker produces a sound wave of constant frequency, which is reflected directly back along its original path by a metal plate approximately 1 meter away. Okay, so to form stationary wave, we have a wave source, then we have a reflector here. Okay, we're going to move a microphone connected to a CRO to identify regions of high sound intensity, loud spots, and quiet spots. The wavelength of sound is determined using the least possible number of measured quantities. Okay. Which row shows the quantity that is needed? Okay. So we have, okay, I'm just going to draw some waves in between. Let's say you have some standing wave here. Okay, so this is your standing wave. You would be able to measure the loud sound here. There's another loud sound here because these are your anti notes. Of course, you could also measure the quiet sounds, which are your notes. Also can. All right. And we want to find the wavelength of sound. So in order to find the wavelength of sound, if you look at my shape here, isn't, like for example, antinode to antinode, isn't here to here lambda over 2? Or if you want to take node to node, isn't here to here also lambda over 2? So the important thing to take away for stationary wave is antinode to antinode is lambda over 2. Node to node is lambda over 2. So I only need to find the mean separation of the quiet spot. The rest I don't need. So the answer is D. The rest is not needed. Also, if I know the frequency and the speed of sound, I can just VF lambda to find them, which I also don't really need. Okay. So objective questions are different, they're just different. But I don't think it's that difficult. Okay. All right, next one. The same thing for path difference. I think it's the same question there. Okay. So for this one, you are given the value of X distance between bright fringe. You have the distance between the screen and the slits. So we want to find the path difference of light wave at the second order dark fringe. Okay, so I can start from here. 0. Okay, I have no space to draw there. Let me see how they're labeling. 0 order bright fringe, first order dark fringe, second order dark fringe. Okay, so that means by the time I reach here, these are dark fringes. I'm not going to label the bright fringe. First order dark fringe is here. Okay, let me zoom in. Cannot see properly. Okay, so I will label both dark and bright for you now. This one is bright. Path difference is 0. This one is dark. 0.5 lambda. This one is bright. 1 lambda. This one is dark. 1.5 lambda. Okay. So you need to use d sine theta. No, don't use d sine theta. Sorry. When you see double slit, we're going to use x is lambda d over a, or lambda is ax over d. Okay, so we find lambda first. Okay, I have the slit separation. Slit separation here is too narrow slit. Okay, this one is a slit separation, 0.10 mm. A. So 0.10 mm. The X is 8 mm. And then the D is 2. So you can find lambda. Looks like lambda is 4.0 times 10 to the power negative 7. Okay, but we want second order dark fringe, which is 1.5 lambda. So second order, your delta L is 1.5 lambda. So 1.5 times 4 is 6.0. So the answer will be C. Okay. Okay, another one. This one, you need to state the equation and test them. So this is a wire extended by different forces, and the wire obeys Hooke's law. Okay, just because the wire obeys Hooke's law, I already know F is proportional to X, or F is equal to Kx. So extension and force and extension, you can throw away already. Okay, so now what I have left is elastic potential, energy, and extension. So I need another equation, which is E is equal to half Kx squared. So this means if I plot a graph of E against X, because it's X squared, I'll get this shape. When I flip the axis, it's as if I'm looking for the F inverse X. If this is Fx, this is F inverse X. When I flip the axis, aka I do a reflection along the X equal to Y. Or if let's say you don't know maths or you don't do that much maths, basically the shape will flip like this. Because now you're plotting the graph of X is equal to 2 over K root E. So you're plotting a graph of Y equal to root X. So on the y-axis, on the vertical axis, it will be extension. And then on the horizontal axis, or the x-axis, it will be elastic potential energy. Okay? Okay, so we will continue with today's class. I think I've answered all your questions. I hope it benefits the rest as well. We will see the participants. Okay, so we'll continue to look at chapter 3 today. So, okay, so I generally would recommend that, especially for your weaker chapters, now is a good time to work through the topicals. Okay, so obviously I'm not going to do all the questions in the topicals. The point is less of me doing the question, because if I do the question, you know I can do, right? But that's not the point, ma. The point here is that you should also be able to do the questions. So since nobody is asking questions from the earlier chapters, can I assume that you are okay? Can skip to chapter 7. Okay, now I shall not make the assumption because I know Asian countries are very quiet. People rarely speak their mind. But don't feel shy. Don't be that shy. If you don't say what you want, I wouldn't know. Wouldn't know what you want. So yeah, it's a group class. Can make it work for you as well. Let me know what are the requirements or the things that you may need. Okay. So, right. So today we're going to look at chapter 3, which is dynamics part 1. Okay. And I like to think about chapter 3 and chapter 4 as a long chapter that is tied together. Okay. Because we want to try to do a few things in chapter 3 and 4. Okay. So in chapter 2, we learn to describe motion. Okay, so I'll make a note here. Chapter 2, kinematics, the focus is on describing motion. So we use terms like displacement, velocity, and acceleration. Okay, and then now in chapter 3, and also later in chapter 4, so this is going to be a very big mind map, we are going to look at first the why of motion, and then in chapter 4, the effects of motion. So in chapter 3, we're going to learn Newton's law. Probably should move here so I got a bit more space and zoom out. Okay, so we're going to look at the y of motion. So we want to be able to understand the behavior of forces. Think about it as a rule to decide when does force exist and how does it exist. Okay, and then later in chapter 4, we are going to look at the what of motion. Okay, this one we want to study the effects of forces. So you can treat force as like a phenomena that we need to properly define in sciences, chapter 3, so that we can study the effects that we actually see in our daily life. So there are a lot of things that happen, obviously, because a force acts on something. Okay, maybe the thing change shape, or maybe the thing accelerate. So we can see the effects of those forces if we understand what are the rules or what are the laws that the force behave by. Okay, so it's a little bit like, oh, I see an object is moving like that. It is the effect of a force. But before I can talk about that force, I need to understand the law or the behavior of that force. All right, so they are linked together, and generally speaking, they are normally taught together. Okay, so we're going to start first by thinking about your 3 Newton's law, like really understanding what is it about. Okay, so Newton's first law, we're going to call it N1, okay, is about a body, is about something that has something to do with the motion and how it doesn't change. So you can think about it as a law of inertia. Okay, so a body continues its motion, whether it's at rest or constant velocity, unless acted on by an external force. So under Newton's first law, there are ideas of what is inertia and what is mass. Okay, so then scientists begin to think, to change the motion of an object, we require force, because an object will continue its motion unless acted on by an external force. But how do I measure this motion? I will use the physical quantity momentum. Because to change the motion is not as simple as just, oh, this thing is moving so fast or this thing is moving slowly. Okay, so for example, fast objects are harder to stop and slow objects are easier to stop. The second thing that affects motion is the mass itself. Things with larger mass is harder to stop. Things with a lighter mass is easier to stop. Okay, so intuitively, we already know this, which brings us to the second law. Now, the second law tells us that, technically speaking, motion will change when there is an external force. So, number 1, if motion changes, momentum will change. So first law says that object will continue the way it's moving unless acted on by an external force. So now this tells me if the motion change, it means the momentum will change. It means that there is resultant force. So this resultant force, okay, says that, from Newton's second law says that this force is directly proportional to the rate of change of momentum. So the idea here is, number 1, object won't change momentum. Instead of motion, we start to use the word momentum. Object won't change momentum unless acted on by an external force. First law. Momentum don't change unless got external force. Sounds very familiar, right? Okay. Second law, if the momentum change, then the rate of change of momentum is directly proportional to the force. Meaning, if I want to change the momentum more, or if I want to change the momentum faster, I will need more force. Kind of makes sense, right? So the more change that is happening, the more force is required. Okay, so this means if I want to define Newton's second law, this gray color box is the definition. Okay, but because we assume that the proportionality constant is 1, not we assume lah, Newton already defined for us is 1. So force is straight away rate of change of momentum, or dp dt. So you want to define force, you use this equation. Force is equal to rate of change of momentum. You want to define Newton's second law, then you use proportional. This one is about depending on what definition they ask you. If they ask for force, you write equal. If they ask for Newton's second law, you write proportional. Force is no more ma. It is rate of change of momentum. Okay. So this means if I want to define force, because in physics we sometimes don't deal with the calculus lah, we just leave it in the definition. So you can just take the change in momentum over the change in time. This is not a new equation. Okay. But whenever I see dp dt, I think about the fact that I have two graphs. Okay. And the first graph that I can think about is P over T, or P against T. If I have a PT graph and F is dP dt, then the gradient of this graph, gradient is dP dt, right? So gradient is equal to force. Okay. And then the second graph is to change and talk about force against time. And let's say I have this graph. Okay. So this means if I want to find the area, maybe let's say from 1 second to, I don't know, 4 seconds, this is my area. Area is integration of f dt. Or if you don't want to think about too much calculus, it can be seen as the change. I need to write this with a thicker pen. Change in momentum, which is also known as impulse. Okay. So because you take force multiplied by time when you look for area, this makes this unit Newton second. But obviously this unit is force, right? So it's Newton. Okay, it is also a vector quantity. So this is the very first part or very first half of the chapter, right? Where force is the rate of change of momentum, and occasionally you'll be asked to use graph to find that change in momentum. Okay, so we will do, I think we'll do a question now before we talk about the different case study and also your Newton's third law. Okay, so we're gonna try a few questions about the graph. So we'll start first by looking at page 25 in your paper 2 handout. So if you're using a topical, then page 25. Okay, so the first one, you're asked to define momentum. So this is the product of mass and velocity. Okay, and you have two balls, X and Y, same size, different masses. Okay, they're about to collide with each other with the same speed. Okay, and this is the force against time graph of Y exerted on ball Y by ball X. So maybe I'll draw Y. Y is this one. So I'm ball Y, and when X collide with me, I will experience this force. Okay, so the force will press down on Y. The reason why the force increase then decrease is because oftentimes when collision happens, you will expect to see a deformation. So you expect to see a deformation that looks kind of like this. So the ball is compressed, 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 and the ball expand back. So during this deformation, right, the force will increase, 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 maximum, decrease, 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 zero. So the force increase, 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 maximum, decrease, decrease, zero. Sometimes it's a curve, sometimes it's a straight line, but we expect the force to change as the ball compresses when it is colliding. Okay, so part one is a bonus question because you're asked to calculate the kinetic energy of the ball, which should be fairly straightforward. Before collision, ball X have the mass of 0.24 and the speed is 2.3. So hopefully you've come to realize that paper 2 is the easier paper. In fact, it's the easiest paper in your syllabus. So you should try to score as high as you can. So 0.63, everything is given to 2SF, so I'm sticking to 2SF. All right, next. Look at how nice this question is. The area enclosed by the line and the time axis represents the change in momentum of ball Y. So although they don't need you tell you this, but you should know that area is equal to change in momentum. But since they are so nice to tell you, then you can find the change in momentum yourself. Okay. So from here, if I want to look for the area, I will take half times base times height. And this height here is 2, 4, 6, 8, 10, 240. So half times 240 times the base, which is 5. So 600. Okay, calculate the magnitude of the velocity of ball Y of the collision. So to find the change in momentum of Y, I will take the final momentum minus the initial momentum. Okay, P final minus P initial. Tablet went a bit nuts. Okay, so this is 600. I know the mass of ball Y, 0.12. I can find the final speed, and the initial speed is 2.3. Now, before I simply substitute, I have to ask myself, do I expect ball Y to slow down or speed up? Because at the end of the day, this ball Y is going to travel at a speed of 2.3 meter per second. So I actually expect it to slow down because the force is acting in the opposite direction. It may even change direction, I don't know, but it should slow down, okay? Or basically, it cannot be faster than 2.3 lah. It can change direction, sure, but it cannot be faster than 2.3. Another way to look at it is the direction of force is here in the positive direction, meaning the impulse or the change in momentum is also in the positive direction. So this 600 gives a positive, but what about the 2.3? Negative. So be careful, you are still dealing with vectors, meaning this should be negative 2.3. If you forgot the negative sign, you will realize that, hey, the value is a bit too big. So numbers are kind of big. So if you press your calculator, right, you realize that this one is 5,000. So do you stop here? Do you continue? Cannot lah. Because if you put this one as 5,000, right, this is V plus 2.3. This makes even less sense, okay? because like 2.3 here and 5,000 here, none of this makes sense. Then you have to check because this is values are too big or values are too small. So the checking here should happen at did I convert or did I forget to convert or include a prefix? Is there a conversion error? So if you can recall, there is a prefix here. So a lot of times this prefix is missing or forgotten by people. Don't forget the prefix. So if let's say you realize that the prefix is missing, then you're thinking, do I rub everything? No, 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 don't rub everything. So this is milli, right? So you times 10 to the power of -3. So this one will be 600 times 10 to the power of -3, which is 0.60. So this one you can cross out during the exam, 0.60. Remember that this should always be two significant figures. So if you write 0.6, this is wrong. You will lose 1 mark. Okay, then which means here, so I'm just showing you as if I reach this point that I realize, hey, something is wrong. So I can put 0.60 on top here. It's not really a problem. Okay, which means this value will now be 5. Okay, lor. So now my V would be 2.7. Okay, so don't waste time to correct everything if it's a conversion or prefix error. The beauty of the prefix is you can add it at the back of your calculation, and maybe you only need to cross out 1 or 2 lines of your final answer. Okay, hopefully we won't make that mistake, but also making mistake is human, so it's totally okay. All right, next, we're going to draw a graph of the force that Fx exerted on x by y. Okay, this is my ball x. During the collision, y will press down. So this is obviously in the negative direction. I expect to get a negative graph. And because Newton's third law says that the force must be equal magnitude and opposite direction, so I'm just going to do a reflection of the graph. So here to here, reflect this. Then the other side be to do this. So we're just copying the whole graph back to back. Okay, so again, I can draw y here for you. So the force of y is in this direction. So these two are your action-reaction pair. Newton's third law, force pair. Okay, so now we're going to look at some objective questions regarding these graphs, the force, time, and the momentum time graphs. And I know, obviously, we can talk about conservation of momentum here, but later lah. So here you can tell that because there is force, there is change in momentum. If the force is 0, the graph is going to be flat. There'll be no area, so there'll be no change in momentum. Because there's change in momentum, there's a change in velocity. Okay. If you feel like it, you can even use conservation of momentum to find the velocity of the other ball and double check. Okay, so you know what, let's do that. So you can use the sum of the initial momentum is the sum of the final momentum. I'm going to do it near the diagrams that I can easily sub the values in. So the initial momentum is 0.24 times 2.3 plus 0.24, 0.12 times negative 2.3. So This will make this zero 0.627, sorry, 276 on the other side, on one side. And then on the other side, we sort of know, maybe we're looking for the speed of ball x. So this one would be Vx plus, I'm going to move it a little bit here. Zero 0.12. We already know the speed, which is 2.7. Although I think it's rounded. No, it's not rounded. Okay. So what is 0.24 Vx plus 0.324. This 2.7 is positive, so it changes direction. Okay. So this will be negative 0.048 is 0.24 Vx. You can find your Vx. That would be negative 0.20 meter per second. So I think what I would like to do now is to show you how the conservation of momentum plays out. So I'm going to copy this so I have a bit more space. I'm going to do it at the side. Hang on. Here. Not to forget, this was our initial situation. Look something like this. This is before collision. Okay. So now after collision, right? After collision, I know that x will move in the opposite direction because of negative. So x will be forced to change direction a bit slowly. And y has also changed direction because it's positive 2.7. They're basically reverse direction. Okay. In fact, you can even check this using the change in momentum of x. So mv minus m. So the mass is 0.24. The speed is negative 2.0 minus the initial speed is 2.3. 0.24 times 0. This would be negative 0.60. You realize that this is also the change, meaning the change in momentum of x is negative 0.60 Newton second. So x will experience a force in this direction, in the negative direction. The change in momentum on y is positive 0.60 Newton second. Because y is in the positive direction, this is the positive direction. Okay. Another way that we managed to show this is by drawing the graph of the force on x, negative direction, and then the force on y, which is the positive direction, but is mirrored. This is force, this is x, xt. So change in momentum is the same because it's area under the graph. Okay. So right now, right, another graph to draw here is the graph of momentum against time. But if I want to draw to scale, because this one is in millisecond, it's going to look very weird. I will not draw it to scale. So I'm not going to draw underneath. Momentum against time. Okay, so the momentum of the initial momentum of x is 0.24 times 2.3. Let me quickly calculate this for you. This one would be 0.552 positive. And then it collides, then it drops. Okay, if I really care about the shape of the graph to follow that triangle, then the gradient should look like this. It's kind of weird lah, so I'm not going to bother. I'm just going to draw a straight line. Okay, then it goes into the negative region. So this is the momentum of x. This would be 0.24 times 0.2. So this is 0.048. Negative 0.2. So the change in momentum of x is here to here, negative 0.60 Newton second. Newton. If I want to draw another graph for y starts off with 0.24, sorry, 0.12 times negative 2.3. So that will give it negative 2.7. We'll draw a bit longer. It'll be here. Negative 0.276. Somewhere. It's not really drawn to scale, okay? And then eventually it will level up to the positive region, 0.324. So somewhere here. So the momentum for y has increased by 0.6. So this is so-called conservation of momentum. The momentum of x has decreased by 0.6. And where did the 0.6 go? It went to y. Okay, so the important ideas here is, number one, the change in momentum of x is the same as the change in momentum of y, but with a negative. 1 plus 0.6, 1 minus 0.6. Okay, so because of this, let's say there are two ways to open it up. Let's say the first way, I think about forces. Okay, so the change in momentum of x is equal to negative change in momentum of y, but the change in momentum happened in the same time period. Okay, so the t that we're talking about is this time when it takes to decrease or when it takes to increase, this time interval at the highlighted part in the t-axis, same time. But why is change in momentum over time? From Newton's second law, the force on x is equal to negative force on y. That's why this 2 is Newton's third law, force pair. So collision is the perfect way to show all of your Newton's law. From first law, meaning the object momentum will not change until this point where it experiences an external force now. That is the point here. And when you experience the external force, its momentum changed by 0.6. But if x changes by 0.6, x is being pushed by y. So y also must change by 0.6. Equal magnitude, opposite direction. If you force me to change by 0.6, because y collide with x, then x will also make y change by 0.6. You cannot change something without you being changed at the same time. That's a bit of a philosophy there. Okay. And then here, if I want to find the momentum in x, okay, I will take mx vx minus mx ux. And this is also equal to my uy minus, should take v, my vy minus my uy. Normally, we don't see it in this form one. We will normally put all the u's together and the v's together. So I am going to take all the u's and put them together. Oh wait, there's a negative sign. Hang on. Negative here. Okay, so mx ux go one side becomes positive. Negative, negative becomes positive. My uy. And then on the other side, mx vx is plus my vy. So this looks like sum of the final momentum. And this looks like sum of the initial momentum. So sum of final momentum is sum of initial momentum. This one is conservation of momentum. Okay. So just the fact that the momentum changes by the same amount, I can show two things. Number one, I can show momentum conserve. From the perspective of X, I didn't lose 0.6, I gave it to Y. From the perspective of Y, I didn't gain 0.6, X lost 0.6. So this means momentum is conserved if X and Y are together. Is considered as a system. Means they are together lah. Okay. Whereas in this case, if they are single, if X is a lone system, then obviously the change in momentum is negative 0.60. Momentum not conserved. Means there is a force from Y on X. And the same thing for Y, if Y is a lone system. The change in momentum is positive 0.60 Newton per second. P not conserved. There will be a force from X on Y. So when you think about conservation of momentum, it's important to know how you are applying the conservation law. Are you only applying it on one of the balls? Then momentum is not conserved. Because if X is a single person, then when Y come and push X, Y becomes the external force. But if X and Y are together, then X push Y, Y push X. The force are equal magnitude, opposite direction. There is no external force. If X and Y are considered as a system, there is no external forces. So momentum conserve. Conserve is scientific speak for doesn't change. I wanted to write no change, but then my English teacher school, so it doesn't change. Before and after an incident, if something is conserved, that means it's good. Didn't change. Conserve the environment, etc., etc. All right. So this one is an important thing that they will keep asking because it's one of those like fundamental understanding of physics. And also you can see all three of your Newton's law. Okay. So for questions that are about the graph, I want to just allocate questions at different parts. Okay. So for questions about the graph, from your chapter 3 topical, question about the graph, you can try page 16 and 17. I believe one of these is recorded because it's an important example. So if you In fact, so important that they asked twice a row in different paper sitting. Okay, so if you want a graph about that thing, do this. Then, if you want a question about using change in momentum over time, you can try page 21. And page 18. Then if you want to look at Newton's second law and third law and the conservation thing, page 11. Okay, so try out these questions. Don't be shy to ask me if you don't understand. But if you can do all of this, that means this part is more or less settled. Okay, so now is a good time to take a short break because it's been an hour of sitting down. Don't sit for so long. But when we come back, we will start looking at some objective question. And then I want to open up a little bit more of regarding this change in momentum over time. Yeah. So momentum is the same if there's no external force. If there's force, we can find that force using change in momentum over time. And we're going to look at a few case studies involving that after trying some objective questions. So if you want to try some during the break also can, but I'll see you in 10 minutes. Let me pause the recording again. Okay, so we stopped at the idea of force is rate of change of momentum. Okay, and I think we'll do some objective questions before we proceed, just to showcase this relationship further. Rate of change of momentum or change in momentum per unit time. Okay, so for example, for this one, you're given a momentum time graph. Okay, and you are asked basically what is the meaning of the gradient of the graph. Okay, so it's pretty straightforward here because this is a momentum graph. So the gradient itself is dp over dt. So this would be the resultant force on the car. Okay, the rest is just there to debate you. Don't be debated. You must hold firm. Force is rate of change of momentum. Okay, so this is another question on page 40. Here you are given many momentum time graphs. So it's still the momentum time graph, yeah? And it says here that we have a constant resultant force. So if F is constant and F is dp dt, so constant F, constant gradient. So the constant gradient is d. Okay. So graph questions doesn't have to be complicated. It can be fairly straightforward. Okay, let's move on to a question. Okay, so for this one, it says that you have a ball M, or statement question. It's a statement equation question. Okay, traveling vertical downwards. So it's going to hit the ground, hit the horizontal floor at a speed u. Okay, so this is u traveling downwards. It rebounds vertically upwards. So imagine this is the same line, but I draw on the side so I can see. It rebounds with a velocity v. What is the average resultant force? So from here, resultant force is change in momentum over time. Okay, so since I already draw the picture, it's, I guess, pretty obvious which one is initial and which one is final. Okay, so to find the change in momentum, I will always take the final minus the initial. And then it says here the collision lasts for delta t, so I guess I can just put delta t. M is p. So this means, right, if I want to find the change in momentum, I'll look at my final momentum, and maybe I need to decide, not maybe, I do need to decide which direction is positive and which direction is negative. So obviously the easiest one is to just take up as positive and down as negative lah. Okay, so this would be mv minus m negative u over delta t. So I have mv plus mu over delta t. So the minus 1 is wrong. Okay, change of momentum, although here we minus, you also need to remember that momentum are vectors. So whenever we swap direction, the negative should also come together. Drawing a diagram will help remind you whether and if to put a negative, okay? Yeah. So next thing, we need to decide whether the force is upwards or downwards. Well, in this case, right, if you look at this thing is have to be positive, right? The mv plus mu over delta t. This whole thing is always positive. How do I know? Because, well, the thing that is supposed to be negative, I've already included in the sign, and everything else here is positive. So it should be upwards because we took upwards as positive. Okay. Another way to look at it is the ball fall down and change direction there. Surely there is a force pushing the ball in this direction. If not, how did the ball end up going up this way? So surely the force is pushing the ball away so that the ball changes direction. You can also use, I guess, logic. Okay. All right. Number 7. So once again, we encounter the momentum time graph, right? So you could think of the momentum time graph as something that is fairly popular, but it says here that the resultant force is increased slowly. So if resultant force is increased slowly, this means gradient is getting steeper slowly. But basically, we need the gradient that gets steeper and steeper. This gradient is getting less and less steep. Nope. This gradient is getting less and less steep. Nope. So the answer is B. It's getting steeper and steeper. But you could say, teacher, but why does the momentum decrease, although there is a resultant force that is increasing? Well, this means that the object is moving in a particular direction. Let's say the object is moving in this direction. This is my B. But my force is acting in this direction. And in fact, my force is acting larger and larger in the opposite direction. Like I'm pressing a brake harder and harder. Okay, so this means the velocity will slow down more and more, drop faster and faster. Okay, so just because the resultant force is increasing, it doesn't mean that the momentum must increase. So this would be a corresponding for this one. Okay, whereas for these two, this one, if you really want to draw, so just as a practice, this momentum is increasing. So let's assume that the object is traveling to the right. This means that my force is also pulling to the right, but the force is pulling less and less. Okay. That's why the momentum can increase. Okay. So for C, the momentum is decreasing. So although I'm going to draw some smoke trail to represent the direction of V, this means that my force start off very large and then it decrease and decrease. Okay, whereas this one is just constant force in the same direction of velocity. What's this one? Because obviously the object will move faster and faster, but the force is constant. Okay, so it is pretty common for us to be a little bit confused about what is force and what is velocity. So you gotta think carefully in your mind. Velocity is about the motion of the particle. How is the particle moving? Okay. And force is about the change in motion. So for example, in option D, the particle is just going to move faster and faster at constant acceleration. So for this one, you can see constant F, constant A, because F equal ma, question mark. Okay, we'll talk about this a bit later. And then for all of the other cases, the force keep changing, so the gradient have to change. So in other words, right, whenever you are not sure about whether which graph it is, because you don't have context, you don't know which is the direction the object is moving. You also don't know whether it's speeding up or slowing down. Okay, so in this case, use the gradient. Okay, but because I know the difference between velocity and force, I know that they will be in the same direction if the velocity or the momentum increase. I know they will be opposite direction if the momentum decrease. But it doesn't tell me about how the magnitude change. Slowly increase. That means I need to check the gradient to tell me how the magnitude changes. Okay. So yeah, this is the situation. Page 1. Shouldn't the answer be C? Which one? This one? Oh, there are two straight lines, right? Okay, so this one, okay, I didn't read the question properly. Act on the object in the direction of the object velocity. So this is also a nice way to relate to the previous question. Let's say the velocity is in this direction, okay? And then you have a constant force pulling in this direction. So obviously, because they are both same direction, V and F, same direction. So logically, this will tell you that the momentum will increase. So the answer is C, not D. Okay. So when you think about momentum, of course, think carefully about not just the magnitude of the force, but also whether the magnitude is, whether the direction is the same as velocity or not. Okay. So in other words, right, a few pointers here. The gradient, which is dp dt, is linked to the change not really change in momentum, but this one informs me about the force, magnitude of force. Okay, of course, this one is obviously for a PT graph. For FT graph is something different, okay? So this one is the momentum time. And then we would look at the values of P. If it is increasing, so this is an increasing graph. This is an increasing graph, okay? So if the values of P is increasing, then F and V, same direction. You are pulling it the same direction that it is moving, so it will move faster and faster. Okay, and then if it's decreasing, so for this one and this one, F and V, opposite direction. So this kind of question, oftentimes you have to read the question carefully, unless you are teaching, unless you do too many questions already. So try not to only spam the same question from one chapter. Okay, so read it carefully. Try to figure out what shape you want to take, whether it's a straight line or something with a curve. Okay, and then try to figure out whether the direction is the same. So for example, this one says in the direction, so it's the same direction. So we expect the graph to increase. If it's against the direction, then we would expect the answer to be D. I think there's another year where it is against the direction. I don't know lah. There are so many of these questions just lying around. So yeah, you can do them on your own. Okay, so I think the last one I'm going to do regarding the graph is page 35. So here we have a car. Again, it's the same momentum time graph, but it provides a different scenario. It's going to accelerate from rest. So I know D is out because this is not from rest. So from rest means T is equal to 0, V is 0, momentum is 0. So which one shows the variation of momentum of the car? So if it accelerates from rest with constant acceleration, means I will have constant force. Constant force means constant gradient. Constant gradient is B. So this one is decreasing force, decreasing acceleration. This one is increasing force or increasing acceleration. And for D, the force is just 0 lah. Okay, constant speed. So if we know how force is acting, we can also deduce how the motion is changing. Okay, so this brings us to the part where we are now going to unpack this change in momentum over time. We've done several examples already, okay? And the first case that we're going to look at, change in momentum over time, is when the mass is constant. So most of the question that we did just now, the mass is the same. You have a block, you have a ball, moving here, moving there, same mass. So I'm going to unpack this equation a bit. F is equal to change in momentum over change in time. But momentum is equal to, you know what, I'll use dp dt. But momentum is equal to mv. So I can put dp is in place of p, I will put mv divided by t. Okay. So in this case, because m is constant, I can kick out the m and then put in dv over dt. But also at the same time, dv over dt is equal to acceleration. So you end up with your favorite equation, F is equal to ma. You can use this equation if you're very sure that there is constant mass. I write 3 times already. You gotta read the question. Is the mass constant? Most of the time it's very obvious when the mass is not constant, but sometimes people just like this equation too much, you know. F is a vector, A is a vector, so F and A are always same direction. If you pull to the left, obviously the acceleration will be to the left. Okay, so F and A is same direction. It has nothing to do with velocity. It will change the velocity, but the direction on F and A does not depend on the velocity. The change in velocity depends on the direction of F and A. Okay, so F and A is same direction. And also a reminder here, since they are both vectors, always remember to include sign, your plus or your minus sign. Okay. And another thing about this equation is this F is a resultant force. Okay. This one is a resultant force. So obviously we'll be using this equation later, but just a heads up. Okay. This is constant mass. First case. Second case, mass not constant. Constant velocity. Changing mass. So this normal examples that you will see is anything using the propulsion system. So let's say you have a rocket, and then your rocket will push the exhaust fumes down. So the air will come out, and the rocket will lose mass, right? As the rocket go up, it will become less and less mass. So we expect there's this air coming out, so propulsion system. Okay, we'll do a question later, but at the end of the day, we're still going to use d momentum dt. But right now, since v is constant, so I can take out v, and then I have dm over dt. But most of the time, you will not know. All of the time, you will not need to do calculus. Maybe you need to look at some graph or some random paper one question, but we just need to take the change in mass over the change in time. So how much did the mass change in a given time? Did it shoot out, for example, maybe it shoots out the gas at 2 kg per second. Okay, or then you put 2 over 1 here. Or if they put 2 kg per minute, maybe it's a very tiny, it's too tiny. It's a tiny ant rocket. Okay, then you take 2 kg divided by 60 seconds. Okay, it's going to stick to SI. Fun fact, do you know that scientists once convert the petrol or the fuel necessary for a rocket wrongly? The unit conversion was wrong. So it caused the entire rocket to crash. It was a few million USD. Needless say, someone was fired lah, but I just want to point out, even NASA also can convert unit wrongly. Okay. So yeah. So actually, I tend to think that this equation and this equation in my brain is the same thing lah. But either way works. So we're going to look at these two cases. And also, since we're here, I think it's also a good time to just round off everything by defining Newton's third law to you. So I'm going to write Newton's third law here. In this rocket, I can actually show you Newton's third law. So instead of like drawing the air this way, maybe I can draw the air. You imagine the air shooting out this way. I mean, this is obviously an idealized version of the air, but the air will come out this way. I don't know, 2 kg per second. Then it comes out with a certain speed v. Okay. So obviously for this air to shoot out or to fart out, you will need a force here. This force on air by rocket. So if the rocket push the air downward, the air will then say, hi rocket, I'm happy to push you upward. So this force will be the force on rocket, R for rocket, by air. So these two forces are your Newton's third law pair. Okay, so Newton's third law, in a nutshell, is I mean it's here, but if you want the notes to look nice, I will draw it at the side for you. Okay, so Newton's third law basically say that every force acting on an object will cause a reaction force of equal magnitude. So these two forces are the same numbers. If it's 100 Newton, then it's 100 Newton. We have also seen this just now in the paper 2 question that we did. And opposite direction. But it's two other footnotes that I want to point out here in your Newton's third law. Number one, the forces have 4 properties. So maybe I'll put this at the side. So this every force has an equal magnitude and opposite direction thing. This one always talks about the force pair. And the Newton's third law force pair has the following properties. This is especially important when they ask you to identify them. 1, already in the definition, equal magnitude. 2, opposite direction. So definition, we tend to say equal and opposite, but it's not enough because we also need to talk about acting on different bodies. Okay. So if you want to add this third point inside the definition, although it's not needed, you can say every force acting on, object A will cause a react by B, will cause a reaction force on B by A. A push B, B push A. You cannot action reaction with yourself, okay? That's just weird. Okay? And this one is normally shown very obviously in collision. Ball X collide ball Y. Ball Y collide with ball X. So X will push Y in this direction. X on Y. Y will push X in the opposite direction. Y on X. And the final thing about your Newton's third law, number 4, is that it must be the same type of force. So the same type of forces we talk about weight. I like to tell students is WTFN. So I'm just going to list out type of forces here. At least to the relevance of mechanics. WTFN. Weight, tension, friction, normal force. Okay. So sometimes this is normally objective questions. They will ask you, which of the diagram shows Newton's third law pair? Or which of the following forces are force pairs? And then they can give you like a very long statement. Like the whole question is like 10 sentences. So you slowly read lah. Okay. Identify them using these 4 properties. I think 1 and 2, no problem. It is the 3 and 4 that sometimes got problem. Because equal magnitude and opposite direction can be equilibrium, okay? So if let's say I have a box like that, and I pull the box 10 Newton to the left, and I pull the box 10 Newton to the right, this 2 is not Newton's third law. And then let's say it is 3 Newton weight, and then you got normal reaction 3 Newton. All of this is not Newton's third law because they act on the same body, which is the box. The box is like, bruh, why you pull me like that? But this is equilibrium, equal magnitude, opposite direction. But they don't act on different body, and they're probably different type of forces. And even if it's the same, as long as it's act on the same body, which is the same box, so it's not Newton's third. Okay. Again, if you miss out certain things, I print out everything inside Google Drive one. Then you can refer to it later when you have time or when you want to update your notes. Anyway, just print this whole thing, throw into the chat. Well, go ahead and do some questions. What is looking of the last question? This one, I presume. Just want to send it into chat. Okay, we're going to focus on triangle questions for F equal to MA, and also doing 1 or 2 proportion question before we call it a night. Yeah, let's go. All right. Paper 2. I think we will look at what choose the proportion questions. It's only chose 1. Okay, lah. We'll look at page 26. Page 26. Okay, so here we have a bunch of water hitting the wall at right angles. Very strange, but okay. And then it has this density. So normally proportion question will start with density. And also this cross-sectional area. So it's going to hit it at a velocity of 5 meters per second. Then after that, the water is just going to immediately run down the wall. So I guess all the momentum is gone. Show that over a time of 1.6 seconds, this is strangely specific, the mass of the water hitting the wall is 1.2 kg. Okay, so I need to think about this water column like a cylinder. In fact, they purposely draw a cylinder like that for you so you can brain it. I have the area there, but I wonder what is this length? So I got to find the length first because then I can find the volume, then I can find the mass using density. Okay, so I know that the speed is 5 meters per second. Okay, so L will be equal to 5 meter every second multiplied by 1.6 second. So I can find the value of L like this. 8 meter. Then to find mass, I can take density is mass over volume. So mass is density times volume. Put the value of density inside. 1.0 times 10 to the power of 3. Volume is the area, 1.5 times 10 to the power of -4 multiplied by the length, which is 8. So this would be exactly 1.2 kg. So 1 mark is when you find the length of the water column. Then the other mark is when you substitute everything in using the density is mass over volume equation. Okay, so part B, calculate the decrease in horizontal momentum of the water. So this one is obviously still a change in momentum question. So I can take mv minus mu, okay? But the final velocity of the water is 0 because the water is going to hit like that at 5 and then it run down here, but there is no more horizontal speed. Initial is 5, lah. Final is none, 0, because the water just totally changed direction already. So we take it in the horizontal plane. So this would be minus 1.2 times 5 meter per second. So obviously it'll be negative to show the decrease, but this is -6. I'll put 6.0 because once again, I just want to remind you that this have to be in 2SF. No matter how nice your number, 2SF. Okay, because all the data given is 2SF. So if I'm a bit paranoid, intermediate answers should be fine, but I'm also going to put 8.0 here. Every time I read the marks, the examiner report, they nag and nag and nag about SF. Okay lah, so we also care about SF. Right, part 2, the magnitude of horizontal force exerted on the water by the wall. On the water by the wall. So force is a change in horizontal momentum divided by time. So this will be 6.0. And the time is 1.6 seconds. Divided by 1.6. This will be 3.75 Newton. Roughly about 400 grams of force. You could also write 3.8 if you want to stick to the 2SFT. Because all the data is 2SF, so your answer should be 2 or 3SF if you want. Okay, so finally, force is change in momentum over time. This part is basically asking you to state and explain the magnitude of the force exerted on the wall by the water. So this is force exerted on the water by the on water by wall. So imagine this is the water column. It experiences a force from the wall. And then after the wall slapped the water can only flow down. Okay. But of course, you know, the power washing concept. If now I look at the wall and this thing together, if there is a force of the wall, then there must be a force on the water. So you want to state and explain the magnitude of the horizontal force exerted on the wall by the water, then it'll be the same magnitude is 3.8 Newton, because this force and the force exerted on the water are Newton's third law. Force pair with equal magnitude. No need to talk about the direction because they didn't ask you to state the direction. Okay, so if you mention in the you just copy the answer and then you explain these are Newton's third law force pair is good enough. Next, we want to calculate the pressure. Obviously, pressure is force over area. So we have that 3.8 and then divided by what is the area? Divided by 1.5 times 10 to the power -4. So this is 25000 Pascal. I want to put 25333 also can, but I am just going to stick to SF. Or even better, writing this in prefix. Okay, so you cannot say momentum is conserved for part C because momentum is not conserved for the water. So you need to mention that it is Newton's third law. Okay, conservation of momentum is a consequence of Newton's third law. Okay, so you can say due to Newton's third law, They have equal magnitude, so 3.8 Newton. Don't have to mention the conservation of momentum. The important word is to mention Newton's third law. All right. Okay. So I'm not sure why I didn't choose certain questions. I guess I can choose them now. So for more propulsion questions, list them down. I'll put them in a different chart. No. Okay. Okay. The reason why I didn't include them is because I think they are both recorded because they're important questions. But if you haven't tried them yet, you should do so. Propulsion questions. 18P22, page 14. Especially this one. There's a little bit of a jump scare in this question. What can I say? They like to tell you to expect the unexpected. So another one that we can think about is the pretty popular platform question. I'm guessing most of the time you will see a similar diagram like this. And this one has been a while since they asked something that is like so. So who knows? Maybe it's in the near future. Page 22 if you're looking at the paper one hand up. Okay. So here is another example of basically there's some water or some air flowing out. And it says that the flow rate is 40 kg per second. Okay. The resultant vertical force on the platform is 0. So I'm going to draw the forces acting on the platform. Okay. So the platform obviously have the combined weight of the man and the platform, W, but the platform is constant height. This means that there has to be a force pushing up on the platform. So this is the force of the water on platform. So according to Newton's third law, if there's a force of the water on the platform, there must be a force of platform on water. So the water is being pushed out, very much like the whole spring, the wall like that. So the wall question was, water press the wall press the water. In this case, water press the platform upwards, platform pushes the water out downwards. Okay, so we want to find what is the speed of the water leaving the platform. Okay, so I know my dude here is horizontal, so I can say force water on platform must be equal to the weight. So this is mg. But also at the same time, force water on platform is the same as the force of platform on water, because this is Newton's third law. So now if I want to find the force of the platform on the water, I will take the change in momentum of the water divide by time. This is mg. So to find a change in momentum of water, I will take the change in mass, velocity, divide by time. Again, this is for the water. Okay. And then this will be mass of the platform, and the man 96, 9.81. So I know how much mass is coming out, 40 kg in 1 second. Then I can find the velocity. It's a little bit strange because this is not a very common calculation that you tend to do. So it looks a bit weird. But oftentimes when I see per second, or immediately I just think to my brain, I take 1 second, then my life is easier. Because 1 second, the water pumping out is 40 kilograms, which is a lot of water, by the way. It's a strange water jet. So I get my speed as 23.5 meter per second, 24. Okay. So for a question that's similar to this, it requires a bit of practice. So you can look at Winter 20 P13 question 8. This one is page 30. Okay. We're going to do 1 or 2 more objective questions using F equal to MA. But try this one out. If you understand this should also be okay. It's just that the direction of the water has changed, but no big deal. And then I'll end by showing you a quick picture of those movements. Okay, so this one is in page 27. Okay, I want to talk a little bit about the pulley system. They are not that popular. All these questions is not very popular, but because there's so many questions to ask, so you kind of don't really know what they will ask. The change in momentum one is popular, the one that we did before the break time. But this one all just random law. Cannot come out. You go and do more questions. So right now you want to use the pulley system and you're asked to find the acceleration of the block. So obviously M is heavier. So M will accelerate downward, capital M, and lowercase or small m will accelerate upward because it's lighter. Okay. So I can use net force is equal to MA, obviously. So here is straightforward, ma. I can take M plus M times A. Right? So if I want to find acceleration, I know I need to divide by M plus M. So in my brain, I think I want to tembak this one. Because, to find A, I will bring M plus M over and divide. So I tembak B. But just in case you are not a tembak type, then don't tembak. Don't tembak means you guess the answer. Don't guess. We will try to do it legitimately. The force acting down here is weight, which is capital mg. The force acting down here is also weight, but it's lowercase mg. Now, on first sight, you may think, actually B also doesn't look very correct. They are both pointing in the same direction. Shouldn't I add the forces, this mg and this mg together? Well, the answer is no, shouldn't add them together. What you should consider is that you must take F in the direction of A. So F and A must be same direction. Okay. If you cannot, then here's what I suggest. You straighten the pulley. Let me big M. I mean, there is tension here, but because it's the same rope, so it is the same tension. And they will cancel out. Now, when I straighten this weight will point in this direction, mg. And the other weight will point in the opposite direction, small mg. And you check the direction of acceleration. Acceleration for capital M is same direction as W. So this is the direction of A. Acceleration for lowercase m is opposite direction of W. So obviously this is the acceleration of A. So what I did here is I straightened the pulley so that my A is the same direction. This allows me to use the force equation a bit better. So let's say I take the direction of A as positive, meaning this one is positive and this is negative. So this is mg minus mg. If you take the right side as positive, then please put a negative in front of this A. But that would be a bit pain. So, oh well, I got answer. So m minus m multiplied by g divided by m plus n is equal to a. So this is what I mean by you can obviously guess the answer just by starting to write the equation. But just in case all the denominator is capital M plus small m, then please try them out one by one, straighten the pulley. Okay. So in other words, right, whenever using this equation, F and A must be same direction, then positive. Same direction, same sign. Opposite direction, opposite sign. Teacher, what happens if they are not parallel? Well, funny you ask, because here's a question. They are not parallel. But the first thing I'm going to do is I'm going to draw the forces. Okay. So whenever you see a scenario and you never see before, label force. Okay. This is page is this 40. So step 1, I will label the forces. So looks like there is mg here. There's also tension here, but tension is the same as this tension. So they cancel out. But unfortunately, this capital Mg is also pointing downwards. Sadness. So right now, if they are going to accelerate, although I don't know where it's accelerated. Oh, wait, I do know. Mass M accelerate down the slope. Okay, so the direction of acceleration is here, down the slope. And if small m accelerate, it will obviously then now force to accelerate upwards. So now I need to figure out how to use this equation. But keep the forces parallel to acceleration. So the only force that is not parallel to A is mg. And because it's not parallel to A, we will need to resolve. So we will take a component that is parallel to A, obviously, and another component that is perpendicular to the previous component. So think of all the resolution of vector questions that we have did so far. Okay. And then when you transfer the angle, you will know that this is theta. Of course, you may be asking me, how you know this is theta? Well, on the channel, there's a dedicated video to address the geometry of a triangle, or the inclined plane, but I will just quickly write this down for you. Okay. So your weight is this direction, mg. And we want to split one parallel to the inclined plane, perpendicular to the inclined plane. So do you see that weight is 90 degrees here? So this angle, because this is a right angle triangle, will be 90 minus theta. And when I resolve vector, this one must be 90, right? If not, I cannot resolve. No? All my identities cannot be used, which means this angle will be theta, so that this one can maintain 90. Okay, so that means when I resolve, I write beside the angle, this will be mg cos theta. This one would be mg sine theta. I don't use mg cos 90 minus theta because it introduces a slight complication. Okay, so most of the time for inclined plane, if you want your life to be a bit faster in objective question, you should be able to recall that this is mg sine theta. Now I collect all the forces that is parallel to A. You are parallel to your A. You are parallel to your A. I will take the direction of A as positive. So meaning this one gets a negative, tension gets a positive. always take the direction of A as positive. It'll make your life easier. So this will be T minus small mg. Put one side. Okay, plus. You want to straighten also can. I'm just doing the straightening without redrawing because I don't feel like it. Okay, so this is the direction of A. This T is opposite direction of A. So this T gets a negative sign. Okay, this mg is the same direction of A, so it gets a positive sign. So then for the second block, it would be mg sine theta minus t. And then they move together because they are tied by the same string. So obviously this will be m plus m sine theta. I don't know whether you realize, but t and negative t will cancel. So the only thing I have left now is mg sine theta minus small mg is equal to, why I put a sine theta? Sorry, this is A. Okay, that makes sense. Okay, so right now I want it to accelerate. So A must be bigger than 0 or not 0. Accelerate. It says here, mass accelerates. A greater than 0. If it's negative, then the acceleration changed direction already, then that's not the question that we're talking about. Okay, so for A to be greater than 0, m plus m is confirmed positive already, right? So I need this whole thing to be positive also. Mg sine theta minus mg must be greater than 0. Okay, because this m plus m is already positive. So I need the other value on the other side of the equal sign to also be positive so that your A is positive. So obviously I can bring over the g and so-called cancel or divide the whole thing by g. So I got big M sine theta minus M is greater than 0. I look at all my options. It is sine theta on one side. So I'm going to rearrange. And then my sine theta must be greater than small m over capital M. C. Okay. There is a slightly shorter way of doing this objective question, especially since this objective question doesn't actually ask you to substitute values inside. Okay. The slightly shorter way here is to think about the forces. Right now, capital M wants to be dragged down. Capital M wants to go in this direction. Pulling it is mg sine theta. Small m wants to go in the opposite direction. Pulling it is small mg. So if I want it to accelerate down the inclined plane, the force going down, mg sine theta, must be bigger than the force pulling the block up the inclined plane, mg. Can cancel the g. So I get sine theta is equal to m for m. Wow, teacher, so much more faster. Of course lah. If you look at the diagram and you don't panic, you know that you're supposed to resolve. Look at the component that is parallel to acceleration. So sometimes doing physics, right, if you're at the level where you're comfortable, you can see that a lot of things that we do is formal, but not compulsory, especially in objective questions. Okay, formal meaning we always start with Newton's second law. We write down all the forces, F equal to ma, make sure we take care of the sign, and then we consider the scenario and apply accordingly. But you can also do the street fighter way or the gangster way. Meaning I look at this diagram and I'm like, I don't care about the tension. I just want to know whether the inclined plane is steep enough for this capital M to slide down. If it's not steep enough, then the lowercase m will pull the thing up. So I know it's a competition between mg sine theta and mg, small mg. Okay. So a lot of this kind of question requires you to understand that at the end of the day, when you solve and you use this equation, F and A has to be in the same direction, then they have the same sign. Opposite direction, then they have opposite sign. So the allocation of sign is important. So to practice that allocation of sign, actually, if you look at your past year question, there's not that many objective lah. But the Incuvo of the pulley should be prepared. Okay, so you can do May June 22 P12. This one is not really a pulley, but the sign of acceleration is key to understanding this question. And this is a bit of a hard question. So this is page 44. And then another question around the sign is the person, the helicopter. May June 11 P23 question 3. This one is page 2. Chapter 3 P1. Chapter 3 P2. So these two questions will test your ability to apply F equal to MA on slightly different scenarios. Okay. So next week, we will continue with F equal to MA, but we are going to talk about what happens when there is terminal velocity or when there's drag force, because those kind of questions can be a little bit tricky. Okay, then we will round up chapter 3 by talking about collisions. All right, so I generally recommend you send me questions throughout the week. Don't leave until Saturday so that we have more class time to progress the syllabus. But I think it's enough for today so your brain don't explode. Take care. Send me questions throughout the week. I will see you. Good night. You got any questions, just book me on Discord. Okay.